So this class we're going to talk about Newton's method, why we use it, how we use it, and what even brings it up in the first place. So a couple things that we already know, you should already know this, but if I ask you to find the root or the intersection between two functions, the way to do that is first, let's say I give you actually a function f of x, which is x squared, and g of x, which is equal to x. So first, to get an idea of what it looks like, we can just plot it very quickly. We would get that x squared looks like this, and then x looks like that. So we expect to get two intersection points, one here and one here, and by experience, you could probably already tell that this is going to be at 0, 0, and this is going to be at 1, 1. But to find this algebraically, let's say we did not know that, let's just forget this completely. I'm going to erase it. So yeah, I want to find both points. To do that, I would set these to be equal to each other. So x squared is equal to x. Then I would solve for x. So x squared minus x is equal to 0. And then factor out an x. X times x minus 1 is equal to 0. So x must be equal to 0 or 1. And then plug these back into here. So if x is 0, y or g or f of x has to be 0. And if x is 1, then the function must be at 1, 1. So yeah, and those are both of our intersection points, and we are done finding those. Let's say I give you a more difficult kind of intersection to find. What if instead of x squared and x, I say that f of x is equal to x to the power of 5, and g of x is equal to 1 minus x. So you might think, okay, we can do the exact same thing. Let's actually try it. So first, I'll once again draw my plot. And now I can actually start graphing them. So this would be x to the power of 5. It would be kind of like that. Very similar to x to the power of 3, but a bit more flat here. And then for 1 minus x, it would look something like that. So we know that this is at 0, 1. This is at 1, 0. And we are trying to find the intersection point, which is right here. This kind of dot between the white and the yellow lines. We had to find that. So, okay, let's do what we did last time. Let's make these equal. So I can say x to the power of 5 is equal to 1 minus x. And then once again, solve for x. I would get x to the power of 5 plus x minus 1 is equal to 0. And now from here, if you try to do anything at all, it turns out there is no actual good way or nice way of finding what x is. Since this is a power of 5, it is a lot more complex than what anyone should know. And it's actually kind of almost impossible for a human to find it by writing it down. So this is pretty hard to find, which is why the Newton's method became a thing. So this is the formula for the Newton's method. It states that if you give it an initial guess x, and you find what the function is equal to at that value of x, and what the derivative is equal to at that value of x, you get a better guess for that function. So let me repeat that again. If you give it an initial guess, I'm going to do this in yellow. So initial guess, you do stuff with it, with that initial guess, you get a better guess. So for example, if we know that over here in this function, this guess, personally, I would say this is close to 0.5. Because if it's between 0 and 1, we could say 0.5. In reality, it is a bit more because we can kind of see it. 0.5 is kind of here. This is a bit more than 0.5, but 0.5 would be a good guess. And then after that, you plug in 0.5 into xn and plug it here and here to get a better guess of xn plus 1. And if you're kind of confused what the n and n plus 1 mean, I'm going to explain that more when we go to the next example on the next slide. So yeah. Okay, so for our example, let's say my question was find the point of intersection, or basically find the root, in other words, between sine x and 1 minus x. This is f of x, and this is g of x. It doesn't really matter what you call f of x and what g of x is, but yeah, I just chose to name it that way, so that's what we're going to go with. And then, so let's say I graph it once again. If I do graph it, sine x would look something like this, and it goes on forever. And then 1 minus x, I'm going to do it in yellow, it would look something like this. once again, first of all, we know that there is one intersection point because sine x goes back up, kind of like that, but 1 minus x continues to go down. So we know that there's going to be one intersection point, and that's kind of important for more complex stuff. But yeah, you kind of don't need to know that for now. But yeah, so we drew it. We know that sine x is 0, 0 here, and this is equal to 1, 0 on the blue dot. So we know that the intersection must happen between 0 and 1 again, because this is 0, this is 1, intersection is somewhere in between. We do not know where that is yet, so that's what we're trying to find. And once again, let's try to first of all do this with the way we're used to doing it. So let's say sine x is equal to 1 minus x. Let's try solve this. So sine x plus x minus 1 is equal to 0, and we're stuck. There's no way of finding what x is, because if this was a quadratic, we can probably use like the quadratic formula. If it was a linear equation, we could use something just like algebra in general. But if you have sine x, you can't really solve this, and we're stuck. So let's use the Newton's method now. So I'm going to kind of write it down. It basically said that x of n plus 1 is equal to x of n minus f of xn over f derivative of xn. The derivative is really important because it matters a lot here. But yeah, so our function is actually this. We found it when we combined it. So the combining step is actually part of the solution, because this is what we're going to call our new f of x. You have to combine both functions into one new function. So f of x is going to be equal to sine x plus x minus 1. And like I said, we need the derivative at some point. So let's find that now. F derivative of x would be equal to derivative of sine x is cos x, and then derivative of x is 1, derivative of negative 1 is 0, so we're not going to write it down. So as a summary, we just found that f of x is sine x plus x minus 1, and then f derivative of x is cos x plus 1. Now we have kind of all we need to find out a better guess for where the root is. But yeah, so like I said, first I'm going to guess that this approximation is at 0.5. So x is equal to 0.5. That's my initial guess. Try your best to make it as accurate as possible, but in reality, it doesn't really matter unless you don't give it like a value of infinity. But yeah, so as long as it's somewhere close, you should be fine. But yeah, so I'm going to say that my x naught is 0.5. But yeah, so now actually, before I move on, you might wonder what n plus 1 and n are. These are the subscripts for what guess we are on. So our 0th guess, the one that we did not calculate anything for, is 0.5. Then x1 would be a better guess, x2 would be an even better guess, and then so on, until you get to like as many numbers as you want, and that would be the best guess possible. But in reality, there is no best guess possible because you can always go one more. So in summary, the more you do this, the better guess you get. So that's it. And now, yeah, let's actually try to do this. So, like I said, x0 is 0.5. If I write down the formula, we should have x1, because if n is 0, n plus 1 should be 1. But yeah, so x1 is equal to x0 minus f of x0 over f derivative of x0. So let's plug these in. We know all of these because we have everything to actually write it down. F of 0.5 is up here, so we need it. Let's find it now. So if I plug in f of 0.5, I'm going to get sine of 0.5 plus 0.5 minus 1, which is equal to negative 0.0206. I found this using a calculator, so you should do that too, to double check it if you want. And then we also need f derivative of x naught at some point. So f derivative of 0.5 would give us an answer of 1.8776. And once again, the way I found this was I just plugged in 0.5 into x and found the answer. And yeah, so now we have both of these values, which we need. Now let's find x1. So x1 would be equal to 0.5, because x0 is 0.5, minus, we found that f of x0 is negative 0.0206. So let's write that down. So minus 0.0206 on top. And then for the bottom, we know it's going to be the derivative. We found that as well, so which is 1.8776. Let's write that down here. So 1.8776. So yeah, after getting this, all we have to do now is plug it into a calculator. So I get that x1 is equal to 0.510957953. And the reason I don't really round here is because if I round, I lose a lot of accuracy for my next guess. And there's no point of doing that. If you round off your guess, you're getting back to square one. There's no point of rounding at all here. So try to keep as many decimals as possible. But yeah, so a recap. Our initial guess was 0.5. Now our second guess, or a better guess, or a more accurate guess, is this, which is slightly more than 0.5. And if you look back at what we drew, this kind of makes sense. It would be a lot more accurate on decimals or something, so you could try to plug it in there. But 0.5 is somewhere here, and we got that the approximation is a bit more. So far, it seems all good, so let's continue. But yeah, so if I move on, we got x1 is this. So now let's do the exact same thing to get even a better guess. So x2 would be equal to x1 minus f at x1 over f derivative of x1. You can already see this gets a bit repetitive because you just keep plugging in values into the same formula until you keep getting better numbers. So yeah, f of x1, so plug this in here. You should get this in a calculator, but you will get negative 0.00002898. And then f derivative of x1, once again plug this in a calculator again, you should get 1.8722. And yeah, so we got these, we have x1, let's find x2. So x2 would be equal to 0.510957953. Basically, I just plugged in this over here and got this. And then for the other values, we would get minus negative 0.00002898 on top over 1.8722. All I did was I put this here and I put this here, which are the two values that we want to find x2. And yeah, so now plug all of this in a calculator. We should get that x2 is equal to 0.51097387. So let's kind of pause for a second. If you compare values so far, we got that this is x1 and this is x2. If you notice, over here, like after the 9, it does get better at x2. So we are still getting bigger of an answer. That means we're getting even closer. Because think back of the graph again, which is over here. Our accurate is still getting closer to the actual intersection point. But yeah, let's repeat this 2 more times because, once again, you can repeat it as many times as you want, but usually like 3 or 4 times is a good stoppage point because it starts to like give us negligible differences after that. But yeah, so let's find x3. x3 would be equal to x2 minus f of x2 over f derivative of x2. F of x2, once again, put this in a calculator. Let me just write that down. Put this in a calculator. You should get that this is equal to 0.00000824. And then f derivative of x2 should give you 1.8723. And let's actually find x3 now. So x3 is equal to 0.51097387. Once again, all this is just x2. And then plug in the values that we got. So minus 0.00000824 over 1.8723. And then put this all in calculator again. You should get that x3 is equal to 0.51097343. Let's compare answers again. So I'm going to actually highlight all the answers that we found so far. We found that x1, I'm going to erase this. But yeah, we found x1 is this. We found x2 is this. And we found x3 is this. If you actually notice what's happening so far, not many numbers are changing. let's actually kind of analyze this. We got 5109 in all of them, and then we got 5, and we got 7 7, and we got 3 3 repeated here, and then since then all these numbers have been changing, the 4 3 and the 8 7. What this tells us is that we are 100% accurate up to this point. There is no way you can get this wrong because this does not change anymore. All the other numbers change after because the accuracy gets more accurate, but that difference of the accuracy isn't actually a lot of difference. So if we compare like x3 minus x2 to find how much difference we're actually making, you will get a number that is less than x to the power of negative 5. Because the first 5 decimal places don't change anymore. Only the ones after that do change. So once again, we know that up to this point, up to the 3s, we are perfectly accurate because the numbers are not changing anymore. So we already know that. So after finding out that basically the accuracy stops here at 510973, we can finally say that the root is at x, which is approximately 0.510973. Once again, because the numbers after this decimal place change in both, but these numbers don't. So these are 100% accurate, and we are done. This is our final root, and if you plug it in on Desmos and use like one of those kind of advanced calculators, which does this like a million times in a second, you would get this value somewhere close to it, and you know you are correct. So yeah, we are done, and this is a good answer to our approximation. So yeah, we are done.